So sigma notation is a notational convention that we will use to express integrals. And Appendix B is in the very back of your textbook. It's literally at the very end. And the homework problems for Appendix B can be found right after Appendix B. So you have to look right in the back of the book. It's after Appendix A, Appendix B, at the very end of the book. So sigma notation is a notational convention used for writing sums, as in addition. So here, when I say a sum, finite or infinite sums, I mean, when we're literally just adding numbers. The concept is not complicated, but the notation, if you haven't seen it before, can be, a little strange at first. And the more we can look at this notation, the better it will get. So one reason it can sometimes be confusing is that sigma notation uses the uppercase Greek letter sigma. So right here, we have the uppercase Greek letter sigma, and that looks weird to us, and sometimes that causes confusion when we see something that looks unfamiliar. But the notation is supposed to help us not make things harder. Why do we use the Greek letter sigma? It's really very simple. The word sigma and the word sum both start with the letter S. And so that's why we're using sigma. Why don't we use a big letter S? So we'll actually use a big letter S for something else later on down the line. Actually, the integral symbol, if you look at an integral symbol, so that's an integral symbol. This is actually a stylized letter S, a big letter S for a sum, because the integral is doing a special type of sum. So yeah, the sigma is not supposed to make things worse. When I see sigma, that's a reminder to me, that we're doing repeated addition. And so let me show you how this sigma notation convention works. So I want to just start with kind of a toy example. So suppose we have 10 numbers. A1, A2, A3. So A1 is the first number. Is A1 equal to 1? Not necessarily. A1 can be any number. It's the first, so I call it A sub 1. A sub 2 will be the second number. A sub 3 will be the third number, so on and so forth. We have 10 numbers. I want to add these 10 numbers. I want to do A1 plus A2 plus A3, blah, 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 up to A sub 10. So in sigma notation, we would write it this way. So here, just take a time, just take a couple minutes to really see what you're looking at. And so when I look at this, because I've been doing this a long time, what I immediately see is I first notice the sigma. And so I say in my head, this is an addition. There's going to be repeated addition happening here. Then I notice the I equal to 1. This is the starting point of our addition. I will start at 1. And I is called the index, and I will end at 10. So that's a starting point and ending point. The final question is, okay, what are we adding? That's written right here. The A sub I indicates exactly what we'll be adding. So let me now unwrap this notation. I think it's important to think of this notation like a compressed file, like a zip file or something, and we want to uncompress the notation and figure out what does this notation represent. Okay, so here's the way sigma notation works, is we start with the beginning index value, which is 1. So I'm going to assume I equals 1, and then I'm going to take I equals 1 and plug it into whatever is written here next to the sigma. I'm going to do an example in a second here. This is a very generic example. So here we're just using the notation A sub I for what we're adding. And when I is 1, A sub I just looks like A sub 1. Now this part, when you're expanding a sigma notation, you wouldn't write that part down. That part we would be thinking. I'm starting at I equal to 1, and I'm going to move the index forward. The index here is always made up of integers. So my thought process was when I equals 1, I'm going to take I equal to 1, plug it into here. That gives me A sub 1. That's the first term I'm adding. And then I automatically write down this plus symbol because that's what this big sigma is telling me, that this is a sum, it's repeated addition. So I'm going to write down the plus symbol. And then I advance the index. We were at 1. The next index value will be 2. and I start the game all over again. I look at my index value. So now I pretend I equals 2. I take that, I plug it in to the thing we're adding that's, written next to the sigma symbol. That looks like a sub 2. That's what I write down. And then I write down a plus. I've trained myself in a sigma notation. After I write down the ith term, I then write down a plus. This is repeated addition. And we keep doing this. So that's the I equal to 2 term. So now I push the index forward to I equal to 3, plug it in, write down what we get when you plug in I equal to 3, which is a sub 3, and then I write down a plus symbol. And I keep doing this, in this case, until I equals 10, because in this particular example, we're told to start at 1 and end at 10. Do I have to start at 1? No. Do I have to end at 10? No. Just in this example, that's what I randomly chose to do. So here, eventually you get down to the very last couple of terms, and I equals 9, you have a sub 9. When I equals 10, you have a sub 10. And so what you should see is that this sum, which is a very long expression, we can represent in a very compact form. So the sigma notation is exactly like when we compress a data file. It's really for giving us a compact form that we can use to represent the information. But remember, you have to uncompress the data file to actually find out the information. So I always, tell people to be careful not to get too, the information isn't in the sigma notation. The information is when we expand the sigma notation. This is really the information here. When we write out the sigma notation and say, what does this actually represent? That's the true information. We shouldn't, the sigma notation is just a cosmetic representation of the true information we're trying to, find here. So just as I mentioned, the notation is not supposed to hurt us, it's supposed to help us. So this sigma is there to indicate addition of these a sub I terms. And this letter I is known as the index of summation. These are consecutive integers. In this particular example, we have a starting value of 1 and an ending value of 10. And the actual letter I is not technically a variable. We don't think of it as a variable, but we think of it as a placeholder. And I'll talk about this some more. Why we say I is not a variable is because we already know what I has to equal. I has pre-designated values. In this case, I has to equal 1, then I has to equal 2, then it has to equal 3. So that's what we call an index. Okay, so I want to do a couple of examples because the best way to get into sigma notation is to just do examples. And it's very normal when you're doing something new that it might feel weird, even physically might feel a little strange. Okay, so here, this is something new. We haven't necessarily done math like this before. And so this is going to be a little strange. Okay, so when I see this, I first go, aha, this is a sum because I see the sigma part. And then I go, okay, what am I adding? I'm adding I squared. And I'm going to start at 1 and end at 4. So let's unwrap this notation. So starting with I equal to 1, I take this value of 1. Again, this part, the I equal to 1, that's in parentheses above, I wouldn't write down when expanding sigma notation. This is what I would think. I just want to be explicit here because this is, the first time we're doing it and I'm teaching it. So I just really want to be explicit. So when I equals 1, and I'm, I've been told by the notation Are y'all still there? Sorry, I just got something just weird happened. Okay, I'm sorry. Can you see my screen, everybody? I'll take your silence to be yes. So for the second index here, we're now advancing it to I equal to 2. Plug that into this formula, copy that down here. This is an important part, write down a plus symbol. Now I advance to I equal to 3 and just do the same procedure all over again. I is 3, plug it in. So I write down a 3 squared, write down the plus symbol. And then finally, when I equals 4, I add 4 squared and I stop here because that's what the sigma notation tells me. Start at 1, stop at 4. And so now we can do the sum. 1 squared, that's 1 plus 4 plus 9. Was that 5 plus 9 is 14 plus 16 is 30. So sigma going from 1 to 4 of I squared is a really annoying way of writing 30. And you know, why would we want to do that? You know, we don't need it to express the number 30, but we will use the sigma notation later to represent integrals. So these are sort of toy and baby problems. The point here of this discussion is for us to get used to sigma notation. The concept isn't too bad, but the notation can be a little strange if we're not used to it. So in this case, if we want to compare it to the more generic notation here the a sub I term that we're adding is I squared. That is, I could write a sub I equals I squared. And in this case, you know, I has to be between 1 and 4. This notation here, this notation right here, you can think of this just like function notation. This is very similar to writing f of I equals I squared. And the reason they're writing it in a slightly different way, instead of writing it as a function, that we're writing the input down here as a subscript, there's a kind of a math reason for it. So the math reason is we typically only use this notation, this function notation, when the domain of the input involves real numbers, like the real line. Here, if you look at the index I, the domain here involves integers, which are real numbers, but they're only the integers. There's no real numbers here. We don't allow I, the index, to equal 1.1 or 1.2 or equal pi. The index can only be integers. And so because this is a function where the domain is the integers, we use a different notation convention. We write it like this. It's similar to when we were looking at Newton's method and we had to sequence, and there each sequence is a function of an integer. You know, your first guess, your second guess, your third guess, your fourth guess, those numbers 1, 2, 3, and 4, those are integers. And each guess was kind of a function of that. So here for this second example, we have sigma of I going from 1 to 5. As usual, when I see this notation, I go, aha, we have repeated addition. What are we adding? I'm going to add I. For what values of I? Well, for I starting at 1 and ending at 5. And so now, you know, I just unwrap the notation. We always just start at whatever index value is given here. So I equal to 1. So let me start when I equals 1. I'm going to fix I equal to 1 and plug that value into here. So when I equals 1, I just get 1. And then I do a plus symbol. And then I advance the index. When I equals 2, I plug in a 2 into this expression that we're adding. So here's just I, so I just get back 2, and I write down the 2. And then write down a plus symbol. When I is 3, we get a 3. When I is 4, we get a 4. Here, this index goes all the way to 5. So when I is 5, I plug it in here. I see my last term here of my summation, of my repeated sum is 5. And here, this sigma notation, sigma of I going from 1 to 5, is just another way of writing this sum, 1 plus 2 plus 3 plus 4 plus 5, it's an irritating way of writing 15, right? 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. And again, we're not going to use sigma notation to write the number 15, but we'll use it to represent integrals. And here, the a sub I term that we're adding in this case is just a sub I equal to I. And you should see that kind of as a function notation. Whatever I put down here will go here. So, I hate to do this, but in this case, a sub smiley face would equal smiley face. I hate to do that, but, as opposed to the previous example, where in the previous example, the a sub I was I squared. Here we were given these things. So here the function is just, these are just examples that were given that I basically just made up. So for this next example, it's very similar to the previous example. We're still adding I, but what's different is the starting index here. In the previous example, we started at 1. In this example, you see we're starting at 3. And that was just by my choice. I wanted to make an example where it didn't start at 1. I just wanted to show you something different. So here, this is a sum. I'm going to start at I equal to 3 in this case and go all the way till 5. And what do I do with 3? Well, I assume I equals 3, and then I follow this recipe, whatever it says. In this case, it's a very simple recipe. You just, write down whatever the I value is. So here, this sigma notation just represents 3 plus 4 plus 5. We took I starting at 3, so I plug in the 3, I get 3. At 4, you get 4, and then, when it's 5, I'm just plugging in the I right here. That gives me 5. So again, why would we use sigma notation to write 3 plus 4 plus 5? We wouldn't. This is just an example for us to learn the notation. And here, again, a sub I is equal to I, but the domain is different. In this case, the domain is only 3, 4, 5, as compared to the previous example, where the domain was 1 through 5. So this next example, I say, okay, I see a sigma here. So this is going to be a repeated sum. The index starts at 1. So I'm going to start at 1 and move the index forward by 1 unit until I get to 5. No problem. The final question is, what are we adding? So here, the formula that's given for a sub I is a fixed constant. So for each index value, the output is the same. When I equals 1, the output is a 2. So here, I say, okay, when I is equal to 1, and then I go over here. Oh, well, when I is equal to 1, it just spits out a 2. So that's what I write down. When I is equal to 2, it just spits out a 2. When I equals 3, the function we're adding, it's a constant function. So here, when I equals 3, for example, at this stage here, I plug in it, I look at this, this is a function, there's no I, the output is just a 2, so I get this 2 right here. When I is 4, it's a 2. When I is 5, it's a 2. Here, we've basically added 2 to itself 5 times. So 5 times 2, this sigma notation just represents the number 10. And again, we wouldn't need sigma notation to represent the number 10, but this is a toy example that I want you to practice unwrapping the notation. The way the notation, it works a certain way. And so I want you to practice, unwrapping the notation and using it the way it's supposed to work. You start with the index, plug in the index value, copy that down, slap on a plus, move to the next index value, find the thing you're adding, write that down, slap on a plus, so on and so forth. So I said, in this case, the a sub I is a constant function. For any index value I, the output was always a 2. Last example here. This example connects back up to the first example, and I want to focus on how the index, this letter I, is just a placeholder. It disappears after you expand your notation, the sigma notation. So let's take a look at this one. First of all, what I want you to notice is there's a sigma here, so this is going to be repeated addition. No problem. What are we adding? The k, we're adding k squared, where k will run starting at 1 and it'll end at 4. So I do the same procedure, you know, I say, okay, when k is 1, I'm going to take k equal to 1, plug it into this expression here, and write that down, and that'll give me a 1 squared. Then I do a plus symbol. Then I say when k is 2, what's this expression equal to? It's equal to 2 squared. And when k is 3, it's 3 squared, and when k is 4, it's 4 squared. So when I write out this sigma notation, it's the same as this sigma notation. In fact, both of these just equal the number 30. You can see when we expand out the sigma notation, the index disappears. There's no k up here when we write 1 squared plus 2 squared plus 3 squared. There's no I or k anywhere. When you expand out the sigma notation, the index disappears. That's why I say the index is not a variable, it's just a placeholder. At the end of the day, there are no i's or k's. There's just 1 squared plus 2 squared plus 3 squared plus 4 squared. It just depends, you know, we just have different ways of representing that. So here, the sigma notation of k squared, k going from 1 to 4, is the same as the sigma notation here, sigma of I squared, I going from 1 to 4. That's the same as sigma of m squared, m going from 1 to 4. This sigma notation is not the real information. This sigma notation representation, this is just a cosmetic shell. The real data, the real information is right here. And it's really important when you're looking at sigma notation to understand that. The sigma notation is just a representation for some information. And the way we find the information is by unwrapping the sigma notation. By writing this out, I can get this full form, or writing this out, or writing this out. And all sigma notation works the same way. It's a repeated addition. You're going to add whatever's written next to the sigma. You're going to start at the bottom number. You're going to advance it by 1. The index is always an integer. And you're going to stop at the top number here. That's how you expand out sigma notation, you know, as we've done here or here. So I think it's important on your own to come back to this slide and work through the sigma notation for each of these and to think about how it works. As I said, this part, when I run through the index, this part I'm doing in my mind. You know, I wrote it down for this first example because when I'm teaching here, I want to be very explicit, make sure you know exactly what's going on in this whole procedure. So here, let me do some examples. These are also properties of sigma notation that I'm going to ask you to memorize. But before I ask you to memorize them, I want us to look at them and think about what does the sigma notation represent. So here specifically, I want you to compare the left-hand side and the right-hand side. And even though they're equal, I want you to think about how is the left-hand side different from the right-hand side. On the left-hand side, you know, a good way to think about sigma notation is to kind of start with this part first. On the left-hand side, what we're doing is we're adding the a sub I and the b sub I together first. So we're doing something like this, where we're adding the a sub i's and b sub i's first, and then combining those pairs. On the other side, the order of operations is different. Here, I'm adding the a's first all together, just the a's. And then separately, I'm adding all the b's, just the b's. And then once they're added, then I'm combining the two. The end result is the same, but I want you to compare the notation of how we wrote the two different things. So here's sigma I going from 1 to n of a sub I plus b sub I. So for each fixed I, that's the term I'm expecting to be spit out. So when I equal to 1, when I equal to 2, when I equal to 3, when I equal to 4, so on and so forth, when I equal to n. Here, think of n as a fixed number, like 5 or 4 or 6, some fixed positive integer, fixed integer number. On the other side, here, we're first adding up all the a's, like this thing here. We're first adding up all the a's. And with the second sigma notation here, we're initially adding up all the B terms. And then as a final step, we're adding those two together. As a final step here, we add those two together. Of course, the left-hand side and the right-hand side are equal, but I want you to compare the notational difference. So here, this matches up with this. And this sum here, this sum here matches up with this. As opposed to how this is working. So you want to, the order is different, and you kind of want to appreciate how the notation is reflecting these different things. And certainly this stuff warrants practice. So this is roughly what's called a series. And when we talk about Newton's method, that's an example of a sequence. So in Calc 2, you'll come back to sequences and series in a big way. So you'll see this notation again, and you'll have to deal with all of this stuff again later. So if we can get it now, that's for the best. Again, let's compare these two sigma notations here. So let me say one more thing. At the end of the day, after we've proved this example up here, you really just need to know this property. And it kind of, a way to think about it is we can take this sigma and distribute it to each term. That's kind of a way to think about it if you look at it from left to right. But, that's kind of a shortcut way of thinking about what's really happening. At the end of the day, it's really important to expand out the notation and think about what's happening here, that this sum can be rearranged in this way. And so we can say, the sigma of A plus A sub I plus B sub I equals sigma of A sub I plus sigma of B sub I. For this next one, again, compare what's on the left-hand side to what's written on the right-hand side. Even though they're equal, I want to think about how are they different. So on the left-hand side, we're multiplying each A sub I by C ahead of time, and then adding up all the C A sub I's. So when A is 1, I have C A sub 1. When A is 2, I have C A sub 2, plus ... all the way to C A sub n. So that's what's happening here with this sigma notation. On the other side, the C times sigma A sub I, here we're doing the sum, we're doing this summation first, which involves adding the A sub i's first, and then we multiply by the C on the outside afterwards. So yeah, I know they're equal, but compare the notation, the sigma notations for them, and see how the sigma notation is reflecting this difference in order of operations. And then at the end of the day, I'm going to ask you to memorize essentially this property that if there's a constant on the inside, you can pull the constant out. Here we can pull this constant out. Oops, why did I do that? I keep doing that. No worries, John. Okay, so let me look at the next example. So we have, we've already done an example like this. It's just, it looks a little more complicated because it's written a bit abstractly. So here C is a fixed constant, like maybe 2. Here, remember, N is a fixed constant in all of these, so maybe N is 5. And so here, if you think about what this sigma notation says, it's basically adding C to itself N times. For each of these index values, I equal to 1, I equal to 2, I equal to 3, the output is always C. So here the sigma notation on the left-hand side represents this sum, where for each index value, the output is the same. When I is 1, write down C, plus when I is 2, write down C, plus when I is 3, write down C, ... all the way to when I is N. So here we're adding C to itself N times. So this sigma notation is just a really complicated way of just writing N times C. In the previous example, we had, I think we had 2 added to itself 5 times. So they had sigma I going from 1 to 5 of 2, and it was just 2 plus 2 plus 2 plus 2 plus 2, and it was 5 times 2 or 10. So this is the more abstract version of that. So let me give you two more summation formulas. So these are formulas that calculate the sum for us. So instead of us expanding the sigma notation and doing the addition, this is a shortcut formula. So this first one is a famous one. It's known as Gauss's formula. So here, first look at the sigma notation, sigma of I going from 1 to n. All that represents is we're adding the first n integers. For example, if I was going from 1 to 5, I'd just be trying to find the sum of 1 plus 2 plus 3 plus 4 plus 5, which we know is 15 because that's an example we did. So the formula tells us, rather than calculating the sum explicitly, you can just, it's equal to this formula. So for example, on the previous slide, we had n equal to 5 here. So I'm going to change this n to a 5. Change this n. And we'll calculate and see, do we get the correct answer? So here, if this is a 5, and we're adding up to 5, so here I'm adding 3 and then plus 4. So I do the math, 5 plus 4 is 9, 9 plus 3 is 12, 12 plus 2 is 14, plus 1 is 15. So this side adds up to 15. So let's check the formula. In the formula, I need to plug in n equals 5. So I do 5 times 5 plus 1. 5 plus 1 is 6. 6 times 5 is 30. Here I get 30 over 2. And, not by coincidence, 30 over 2 equals 15. So the formula is a shortcut for having to actually expand out the sigma notation and add it all together. So this is a famous formula here. As I said, it's known by Gauss's, it's known as Gauss's formula. Gauss is attributed with the proof, I think, when he was 7 years old. So Gauss got his PhD by the time he was 16 and was a full professor by the time he was 17. He's one of those overachievers. So let me do the proof. It's a very famous proof. Let me just prove this one. You don't need to know the proof, but it's a very nice proof. And mathematicians are always looking for beautiful, elegant proofs. And this is one of the nicest. So let's call the sum S. Here I'm trying to find the sum of these n first integers. It adds up to something because here you just have, n integers. You're just adding them up. They're all finite numbers. So let's call that sum S. So here, let me expand out the sigma notation here. So S equals the sum of these first n numbers, 1 plus 2 plus 3, all the way to n, the last number. But since the order of addition doesn't matter, 1 plus 2 is the same as 2 plus 1, I also want to write this sum in reverse order. So S would also be equal to the same numbers added together, but in opposite order. So instead of doing 1 plus 2 plus 3 plus 4 plus 5, here I've written it as 5 plus 4 plus 3 plus 2 plus 1. We start with the last number, which is n, and then we subtract 1 until we get to the very first number. Eventually you end at 1. So these are two ways of writing the same sum. So now the trick is, let's add these two. Okay, so I'm going to put a very traditional addition table here. On the top, I have S written as the sum of 1 to n. Underneath, I have S written as the sum from n to 1 in reverse order. And what I want to now do is add the top row to the bottom row. So here, S plus S gives me 2S. S plus S is 2S. Then here I do 1 plus n gives me n plus 1. And here you have 2, which is the second term when you're adding them up in ascending order, plus n minus 1, which is the second term when you're adding them up in descending order. 2 plus n minus 1 is n plus 1. Again, you'll see this pattern. The third terms here, 3 plus n minus 2 is n plus 1. And this goes on for all of them. So your second to the last term here is n minus 1 plus 2 is n plus 1. The very last term here, n plus 1 gives us n plus 1. So if you look, when we add the 2, in this bottom row here, all of these individual terms add up to n plus 1. So this is, this is kind of a crafty, sneaky proof, and Gauss could see this in his mind. that if you kind of fold these numbers back on themselves, they'll add up to n plus 1. And if you keep a tally of how many do we have n terms here. This is the first one. This is the second one. We have n terms. So we're adding n plus 1 to itself n times. So at the end here, I get an equation that looks like this. On the left-hand side, remember we had 2s. On the right-hand side, I have n times n plus 1. So I get this equation that 2s equals n times n plus 1. And remember here, I'm trying to solve for s. So let me divide both sides by 2. When I do that, I get s equals n times n plus 1 over 2. But s is exactly this sigma notation, the sum of the first n integers. So here we get this formula, which is a shortcut formula. On the right-hand side here, what you should see is a constant. Remember, n is a fixed number. For example, n is 5. So then on the right-hand side, you should see 5 times 5 plus 1 over 2. On the right-hand side, you should see a constant where it's all worked out. On the left-hand side, we have a constant. It's still a constant, but it's written in summation form. It hasn't been summed up yet. It's still to be added and combined. This formula does the addition for us. I'll do an example here in 1 second. So we also have a formula for the sum of the squares of the first n integers, sigma I squared. Remember here, this will be a number when you plug in n. N is usually some fixed positive integer. And we have a formula for the sum of the cubes of the first n integers. You do not need to memorize these formulas. You do need to understand how to use them and what they mean. That you should understand that on the left side, I'm adding I, where I starts from 1 and ends at n, where n is some fixed number like 5. And on the right-hand side is the value of that sum. If we did all of the addition, what would it equal? It would equal what's, n times n plus 1 over 2, this expression in the box on the right-hand side here. So let me do an example. So let me start with 2 examples that we did already. We calculated the sum of I squared from 1 to 4. It's 1 plus 2 squared plus 3 squared plus 4 squared. That's 1 plus 4, which is 5, plus 9 is 14, plus 16 is 30. So we calculated that's 30. And we did this one too, the sum of the first 5 integers, 1 plus 2 plus 3 plus 4 plus 5. Right, we said that was 15. So let me calculate these without doing the sum by using the shortcut formula. For this first one, the n here is 4. So in the shortcut formula, which is for the sum of I squared, it's n times n plus 1 times 2n plus 1 over 6. You don't need to memorize that. You'll be given that. I'm going to plug in 4 for the n. And here, these were all originally n's if you look at the formula on the previous slide. And now I do the math. 2 times 4 is 8, plus 1 is 9. 9 times 5 here is 45. 45 times 4 is 180, because it's 45 plus 45, which is 90, plus another 90 is 180. 180 divided by 6 is 30, which is what we showed before. But before we did it the long way. We didn't use a slick formula. But here, the formula allows us to skip the process of expanding the sigma notation and figure out what the sum is. And here for the second one, here the first thing to remember is in this case, n equals 5. And the formula here is this equals n times n plus 1 over 2. So wherever I have an n, I replace it with 5. So here you have 6 times 5 is 30. So this looks like 30 over 2, which equals 15, which is what we calculated the sum of 1 plus 2 plus 3 plus 4 plus 5 is. So I just wanted to verify, at least in these cases, the formula works and it's a shortcut for actually expanding out the sum and calculating it. So this next problem is a little more typical of what we might see. So when you look at the sigma notation, I don't want you to get confused. I want you to remember, aha, there's a sigma for sum. So this is just repeated addition, What are we adding? So this is the part I want to emphasize. Start from the inside. Think about this term here as kind of the center of our sigma notation. I first want to simplify this expression before then using the properties of sigma notation that we looked at on the previous slide. So here, the first step I'm going to do is expand out this part. I've foiled it out. And so that's all the work that's to be done here in the core, this center of the sigma notation. Foil it out. There's no other work to be done. So now I need to start manipulating the sigma part. So we had this property on the previous slide, which said sigma of A sub I plus B sub I equals sigma of A plus sigma of B. So that's what I'm going to use here. Here, instead of A plus I plus B plus I, we have three terms, A, B, and C. So I'm going to take this sigma and distribute it to each term. Sigma of A plus B equals sigma of A plus sigma of B. That's what I'm doing here. So I distribute it to each term, and that's what it looks like here on the left-hand side, once we've distributed the sigma. The next property I'm going to use is we can pull the constant out. We said sigma of C times A sub I equals C times sigma of A sub I. So this constant right here, I'm going to pull it all the way out. This constant right here, I'm going to pull it out of the sigma notation, put it in front. Here, we should think about what this actually means. Sigma of 1, I going from 1 to n. This represents 1 being added to itself n times. When I is 1, we just spit out a 1. When I is 2, it just spits out a 2. When I is 3, it just spits, when I is 2, it just spits out a 1. When I is 3, it just spits out a 1. The function here is constant. For any index value, it just adds up 1. And it does this n times. So this sigma notation actually just adds up to n. So here I pulled out the constant on the first two, and that third sigma, I just went ahead and added it all up and just replaced it. It just adds up quite simply to n. It's just 1 added to itself n times. 1 plus 1 plus 1, n times. So now I have to get rid of the other two sigma notations. My end goal here is to get rid of the sigmas. So I'm going to get rid of this using the shortcut formula. It's equal to n times n plus 1 times 2n plus 1 over 6. You don't need to memorize that. Unfortunately, I have from years and years of doing this. And here I'm going to replace the sigma I going from 1 to n with its formula, which is n times n plus 1. So that's what I do right here. Here is the formula for I squared. Here is the formula for I right here. And then, of course, don't forget this very last term, we had a plus n here, which was this sigma. So I have that right at the end here. And so now we just, add everything together here. I did some simplification. The 4 and the 6, you can cancel a 2. Here, the 4 and the 2, you can cancel. Yeah, so this mess on this side, which is, remember, it's just a sum. It's a sum of n numbers. That will add up to this. Remember, n is a fixed number, like 1 or 5. So for example, if you pick n to be 1, the left-hand side, when n is 1, will add up to 9, because here, when n is 1, there's only one term. 2 plus 1 is 3. 3 squared is 9. And you can check this other side, when n is 1, will also add up to 9. I'll let you check that. But yeah, so here's my conclusion, that this sigma notation, this big mess of a sum, which I don't want to expand and figure out using the shortcut formulas and some properties of sigma notation, I'm able to conclude that that's what it adds up to. That's the final sum. And remember, on the right-hand side, what you should see is a fixed constant. Remember, n is a number that we've already chosen. All right, so I have last two examples here. And this slide is exactly typical to how we are going to be using sigma notation in calculus. So this last slide is really kind of the example of how it'll come into play. So for example, we'll do problems like this. Find the summation of this sum. Figure out what this sum is adding up to. So let me remind you, when you should see the sigma and say, aha, this is a repeated sum. We're going to go from 1 to n. What are we adding? Start with this core. That's what I want to look at, the a sub I here. It looks like 1 over n times quantity I over n squared. Simplify that first. So my first step here is I distribute the square. This square here, I put it on the I in the numerator and the n squared in the denominator. So first I distributed this square. So you see this term. And now I'm going to combine these. N times n squared is n cubed. And write those together. So I've taken this expression and just doing basic algebra, we've simplified it to this point. Now, here comes one subtlety. Remember, n is not a variable. N is actually a fixed number. For example, suppose n was 5. Then this 1 over n cubed would be 1 over 5 cubed or 1 over 125. And our properties of sigma notation tell us that if it's a constant, we can pull it out. Here, the sigma notation only cares about the letter I. If it's not the letter I, the sigma notation treats it as a constant. Here, 1 over n cubed, it's not the letter I, and in fact, n is a constant. N equals, for example, 5 or 3 or 2, whatever. We can pull that 1 over n cubed out of the sigma notation completely. Now, all that remains to be done is for me to get rid of this sigma I squared using the formula. And I'm given the formula. I know, I'm given that the formula for sigma I squared, I going from 1 to n is it equals n times n plus 1 times 2n plus 1 divided by 6. So I use the shortcut formula, get rid of the sigma notation. Last step here is I'm going to do the algebra. I'm going to multiply through that 1 over n cubed. And so here in the denominator, we get 6 over n cubed. So this type of example is typical of the kind of things we'll do. This sigma notation is actually an approximation of an integral. I'll show you on Friday. And so finally, what would we do with this sum that we added? So here, with this sum, a next natural question would be to take the limit as n goes to infinity. And I'll show you why on Friday. So this next example, and I think you should take some time to really let your eyeballs get used to what you're seeing. First of all, you should notice that, okay, I've got a summation here, this sigma notation. So before I do anything, I first need to calculate this sum. I first need to evaluate this sigma notation. What does this add up to? And we did that in the previous example. In the previous example, this is exactly the same sigma notation, not by coincidence. Doing all this math, we can show it adds up to this. So now in the limit, I replace the sum, the sigma notation, with what it adds up to. So here, I've replaced the sigma notation with what it adds up to. And now I take the limit. And here, before I take the limit, I should FOIL out the numerator. And because this is a limit going to infinity, and I'm going to use dominance of powers, I only care about the highest order in the numerator. So I'm just multiplying the highest order terms from each of these factors. N times 2n tells me that the highest order in the numerator is this 2n cubed. So this 2n cubed here is coming from, multiplying these 3 terms. Multiply, and then there's some other terms which are lower order terms. They're n squared or lower. I don't care about those because I'm taking a limit as n goes to infinity. This is giving me an infinity over infinity type indeterminate form, and I'm going to use dominance of powers. So the only part of this I care about is the highest order term, the 2n cubed and the n cubed. And so according to dominance of power, so I'm just looking at the 2n cubed, and sorry, the 6n cubed in the denominator. So you cancel the n cubed in the numerator and denominator, and we get our limit here. When we cancel, we get our limit is 2/6 or 1/3. So this is a bit of a mess, and the notation is irritating, but the concept is not difficult. We just have to practice the notation. The good news is, we will look at this notation and do problems like this again on Friday and again on Monday. So By repetition, you will see it a bunch of times, and it will get better, and it will make sense. Eventually, in Calc 2, you'll just look at the sigma notation and be like, oh yeah, that's just blah blah blah, and you'll just knock it out. All right, folks, I'm going to stop right here.